Okay, here's part two of this problem that we're working on, which is to use the method of Frobenius to solve this particular second order differential equation. And we are working on the singular point 0 there, and it is a regular singular point as we showed on our disgusting green post-it note. And we got into this point where we had taken the derivatives and subbed into the original differential equation. Ta-da-da. And we need to simplify this expression here. So the first thing that I want you to notice is I'm going to label these four pieces: piece A, B, C, and D. And if you look at those four pieces, you see that piece A and C can be combined straight away because, look, I start at n equal to 0, and I have x to the n plus r minus 1 for the exponent there. So I can put those pieces together. Separately now, look at B and D together, and you see that you have something analogous happening here where they start at the same index of 0, and the power is x to the n plus r, and the power is x to the n plus r. So the first thing I'm going to do now to continue to tackle this problem is draw a line. I'm going to take the expression in A and the expression in C, and I'm going to add them together. So if you do that, you will get this little guy. I'm going to take that a little bit farther now. Looking inside here, n plus r, n plus r. I can factor that term out of each of these two pieces here. And I'm not quite done yet. Let me just make sure everything is good. Yes, yes, indeed. I'm going to do one other thing here, which is I'm going to take this term and rewrite this as the product of x to the n minus 1 times x to the r. So I can actually factor x to the r out into the wavefront and write that as an n minus 1 power. And then the very next thing is I'm going to take what's inside of here and simplify it because I'll probably want to do that later. So if I multiply this guy out, that would be 2n plus 2r minus 2 plus 1. And if you put all that back together again, rewrite it all, you get x to the r, sum from n equals 0 to infinity, n plus r times, let's see, what is in here? 2n, 2r minus 1. 2n plus 2r minus 1. C sub n, x to the n minus 1. So we've taken the A and the C expressions and been able to put them together as a single series. Now we're going to take the B and the D and do the same with them. And unfortunately, I've run out of room on that page. So I'm just going to do that. And now let's take B and D and put them together. This one will be a little bit easier because we're just going to take him. We'll have n plus r plus 3, coefficient Cn. And we're going to do the same trick here that we did with splitting up the exponent before. I can split that up as x to the n times x to the r because you'd add the exponents. And I'm just going to pull that little guy all the way out. So here's the sum of b plus d. So if I want a plus b plus c plus d, that's the same thing as add those, add those, and then add everything. So the moral of the story is now what we're going to do is we're going to take these two expressions that we just developed and we want to add these together. So in other words, to keep combining this into a single series now, we need to put this line together with this. We need to add up the two pink boxes. Okay, so on the one hand, I can see that each one of these is being multiplied by an x to the r. Okay, that's fine. That's great. I have no objection to that. And we are both starting at 0. However, the power here is n minus 1 and the power here is n, so I can't directly add those. So because the rule is they have to start at the same place and they also have to have the same powers. And these guys are not agreeing in the powers. So what we'll do with this box right here is we will take this box and we will substitute in here k equal to n minus 1 in the first pink box. So when you do that, I need to get myself a little more working room here. So when you do that, we'll have x to the r out in the front. If k equals n minus 1, then k plus 1 equals n. So if n is 0, then k is minus 1. So we'll start there at minus 1. We'll go to infinity. N plus r will become k plus 1 plus r. My expression inside of here will be 2 times the quantity k plus 1 plus 2r minus 1, c sub k plus 1, x to the k. And now, here's where we're at. Remember what we're still doing here. We're still adding up a plus b plus c plus d. But we've reordered it, so we're doing a plus c plus b plus d. And here is my expression for a plus c that I just reindexed. Let's see, we might as well simplify in there. What do you think? So that will be 2k plus 2r plus 1, c sub k plus 1, x to the k, plus x to the r. Now what we're going to do in this second pink box is now we'll reindex that to k equals n. So this will be the sum from k equals 0 to infinity, k plus r plus 3, c sub k, x to the k. And all of that still equals 0. Then the next thing to do now is we still want to get this down to a single series. And you can see here that now the powers match, but the starting point doesn't match. So what we need to do now is to peel off the single first term in this expression and then have the rest of it starting with k equal to 0. So I'm going to rewrite this first series as, first off, k equals -1. So I would have -1 plus 1 plus r. 2 times -1 plus 2r plus 1, c sub 0, x to the -1 plus the summation from k equals 0 to infinity, k plus 1 plus r, 2k plus 2r plus 1. Oh no, I'm running out of room. C sub k plus 1, x to the k. This is all being multiplied here. And then that is plus this remaining term that's just kind of hanging out for the moment. And this is all in parentheses. Okay, let's clean it up, because believe it or not, we're getting there and we're almost there. So here I have x to the r. Here I have r times, let's see what is going on in there. That will be 2r minus 1, x to the -1, plus, now I'm going to distribute this x to the r. And finally, now you see that each of the two series parts are being multiplied by an x to the r out in the front. So I can actually combine them, and I can rewrite this a little bit if I want to. I can combine the x to the r and the x to the -1. So if I do that, I have x to the r -1 times, oh, somewhere in here I dropped off my c naught. Put them back there. R to r -1 c naught plus x to the r times single summation now, k equals 0 to infinity, the big ugly coefficient here, k plus 1 plus r, 2k plus 2r plus 1, c sub k plus 1, plus k plus r plus 3, c sub k, and that's all times x to the k. And this whole summation is 0. That is a good place for us to take a breath.